there is a theorem that states that the pressure at a point in the fluid is the same in every direction. Pressure is a scalar quantity, not a vector. But even though it is not a vector, the pressure is always perpendicular to the surface. When you have a surface, the pressure will be normal, perpendicular. The pressure will not go like that, inclined, but always perpendicular to the surface. So this is how to prove that the pressure of a point is the same in every direction. So for that, we take a piece of fluid in a space. Let's say that the piece of fluid that I take is in the shape of the right triangle like this. Two-dimensional. It is three-dimensional. You can draw the isometry. But let's see from this two-dimensional view. X to the right and Z vertical. So the pressure here is on the surface P2. On the surface, the pressure is P1. On the surface, the pressure is P3. You know that the pressure is always perpendicular. So you draw perpendicular 90 degrees with this. This one's 90 degrees with the surface. This one 90 degrees with the surface. Now, let's calculate the force due to the pressure. We know that the force is pressure times area. If we calculate the force directed upward to this surface, assuming that the surface here is delta x times delta y, so let's say that the thickness of this right triangle is delta y. So the area of this base is delta x times delta y. The force will be P2 delta x delta y. On this side, we have P1, and the area is delta z times delta y. The force will be P1 times that area, delta y, delta z. Here, you can calculate what is this L. If you have theta, you have L cos theta is delta x, L sin theta is delta z, but the area is L times delta y. So we have all the forces. Now we know that we are in fluid static, which means that this wedge is static. It means we have equilibrium of forces. It means the sum of all forces in every direction will be zero. In the x direction, I have P1 delta y delta z minus P3 sin theta delta y L equal to 0. P1 delta y delta z to the right, positive. This P3 delta y L, if I project to the horizontal plane, it becomes to the left, negative. P3 sin theta delta y L, this one, equal to 0 because we have equilibrium. In the z direction, vertical direction, we have sigma fz equal to 0. So P2 delta x delta y, this one directed upward, minus this one projected to the vertical plane, it becomes P3 delta y L cosine theta is not equal to 0. There is the weight of the fluid. The weight of the fluid is this one, multiply delta x times half delta z times delta y. Delta x, delta y, delta z divided by 2. That is the volume times rho g. That is the weight. Directed downward, so that is negative. So we have these two equations. So simplifying delta y I remove. However, I have delta z, this one, L sin theta. If you have right triangle like this, delta z is L sin theta. So it means this L sin theta here is delta z. So I can cancel that one as well. With that, I write P1 minus P3 equal to 0. That is this one. On the second line, let's cancel delta y, delta y, delta y, delta y. L cos theta is delta x. So it means I can cancel delta X, delta X, delta X. So by the end, I have P2 minus P3 minus half rho G delta Z equal to 0, or this one. From this one equal to P3. We are talking about very small point. So when it is very small, delta Z is 0. When delta Z is 0, this one is 0. When this one is 0 means P2 equal to P3. So if we have P1 equal to P3 and P2 equal to P3, we can say that P1 equal to P2 equal to P3 equal to P. So we prove that at one point in a space, the pressure in any direction is the same.